So today we will discuss time dilation. Okay? Time dilation is one of the consequences of special theory of relativity, and we can say it is also the consequence of Lorentz transformation. So what basically this concept of time dilation says, it says that if a clock is moving with respect to an observer, then the observer will see that the time on that clock flows very slowly. It flows at a very slow rate. So an observer who is at rest and with respect to him a clock is moving, he will observe that on that moving clock the time flows at a slow rate, and on his clock time flows at a usual rate. So we can say basically the measurement of time interval are affected by relative motion between an observer and what is being observed. Okay, but in Galilean transformation we have seen that the time intervals are same in both inertial frames, but it is a different case in case of relativity, when the speed is very high, when speed is very close to the speed of light. In that case the time intervals are not same, they are different in different inertial frames. And time dilation is simply to become large, the time interval becomes large. So let us discuss this concept. For this we will consider a light clock. A light clock basically consists of two mirrors, this upper mirror and this lower mirror. Okay, this mirror is also a sensor. Means it can sense light. When light is incident on this mirror, it will sense that light. So basically in this light clock, which consists of two mirrors, and these two mirrors are separated by a particular distance. Let us say it is separated by a distance L. So this light clock is basically separated by this. These two mirrors are separated by a distance L. This is the separation between the two mirrors. And what happens in this light clock? A light incident, light originates from this mirror. Light originates and it goes in this way, and after reflection from this mirror, it comes back and again strikes the lower mirror. Okay, so the light pulse, it goes from this mirror and then reflects from here and again comes to this mirror back. So this round trip of this light, it takes some time. It will take some time to go from here, then here, and then again here. So it will take some time. So the time taken by this clock to complete this round trip, that is basically this time required to complete this one round trip is basically, we say it is equal to the one tick of this clock. It's equal to one tick of this clock. Now we will say, I will assume that we have two light clocks. हमारे पास दो लाइट क्लॉक्स है. We are having two light clocks. One clock is at rest with respect to you. Let us say that you are observer and one clock is at rest with respect to you. You are sitting here in this lab, so this clock is at rest with respect to you. And there is one more clock that is moving with respect to you. Means that clock is placed in some spacecraft and that spacecraft moves with some velocity v relative to you. Okay, that spacecraft is moving with a relative velocity with respect to you in, say, in x direction, in this direction. So spacecraft is moving in this direction, or we can say in other words that this light clock is moving with respect to you in this direction. So we have two light clocks. One is rest with respect to you and another is in motion with respect to you. See, when this light will come from here, it will reflect from here and again go back to this mirror. So this is called one tick of the light clock. This is called one tick of the clock. So the time taken by this light pulse to complete this round trip, according to you, it takes time t0. Let us say that according to you, it takes time t0 to go from here, then reflect back from here and again come here. So for this, it takes time t0 according to you. So we can find out this time interval. Can we find this time interval? Can you find? See, this light is moving between these two mirrors. We know that speed of light is c. So the light is moving with velocity, speed c. ठीक है ना? So it's moving with speed c, and we know that velocity or speed equals distance upon time. Velocity equals distance upon time. So from here we can calculate time. So time is simply distance upon velocity. So this light pulse takes time t naught according to you, and this time will be equal to the distance covered by light, divided by the velocity of light. So during this round trip, this light covers a distance of twice L naught, because L from here and then L from here. So it covers a distance of twice L. And what is the speed of this light? C. So according to you, this time interval t naught is equal to twice L upon C. So this is the time taken by this light clock to make one tick according to you. On the clock which is at rest related to you. Now we will consider another case. One more thing here. See, this is time interval according to you on a clock which is at rest with respect to you. See, this time interval t naught, this time interval we define as proper time. We define this as proper time. So this t naught is called proper time. Proper time, you can say proper time or proper time interval. It is time interval, it is not a particular time, because light starts from here, then goes here, and then comes back here. So it's a time interval. Okay? This is a time interval. So this time interval is called proper time. So proper time is a time which is measured in a frame of reference in which the clock is at rest with respect to the observer. We can define this proper time in one more way. See, there are two events. First event is that light is originated from this mirror. And second event is that light is absorbed by this mirror. Or we can say light strikes against the mirror. So there are two events. First is that light is incident or light originates from this mirror, and second is that light is absorbed by this mirror. So two events. Now these two events occur at the same place. They occur at the same place because light originates from here and it again strikes at the same point, at this point. It again strikes at this point. Okay, so the two events occur at the same place in this clock. So in this clock, the two events occur at the same place, and this clock is at rest with respect to you, and you are observing this clock. So according to you, these two events occur at the same place. So we can define this proper time in one more way, that is, it's a time that is determined by two events which occur at the same place in a frame of reference. It's the time which is determined by two events which occur at the same place in a frame of reference. Because in your frame of reference, these two events occur at the same place, and the time interval between these two events is called proper time. Okay, it's called proper time. Now we have one more case. In that case, this light clock is moving with respect to you, and we assume that this light clock is moving with respect to you in this direction. Say it's x direction. Okay, let me show you how it is. See, the light basically originates from here, goes here, and then again comes back. So this is one tick of this clock. This is one tick of this clock. So clock ticks each time light hits the sensor. Okay? So clock ticks each time when the light hits the sensor. Okay? So this is one tick of this clock. And this round trip takes time t naught according to you. See, now see, this light originates from here, comes back, and again hits the sensor at this point. So we can say that the two events occur at the same, place, same location in your frame of reference. So this time interval is called proper time. Okay. Now one thing we can calculate is equal to twice 9 upon speed of light, and that comes out to be twice L upon C. So we have represented this as t naught. Delta, irrespective of this delta t, we have represented t naught. So this is called the proper time. So you are at stationary and you are observing this movement. You are stationary and you are observing this movement. Now see, we will consider one more case. in which this light clock is moving in this direction with velocity v. This light clock is moving in this direction with velocity v with respect to u. Again, you are the observer, and with respect to you, this light clock is moving in this direction. You are stationary, but the light clock is moving in this direction. And this light clock will again take, during its motion, it will again make a round trip. See how this round trip, but according to you, this round trip will follow a zigzag path. This time, this light path will follow a zigzag path. It will not follow this path. Basically, it will follow, according to you, it will follow a zigzag path. Let me show you how it will follow a zigzag path. See now, this clock is moving with respect to you. This is the case when the clock is moving with respect to you. So light bounces off centers of mirrors. Here is a bounce हुई थी, ये भी वापस आ जाती है. But in this case, now the light, this clock is moving in x direction. So according to you, you will observe that it will follow a zigzag path, a turn V-shaped path. See, is it following a zigzag path? Is it following a zigzag path? Let me show you how it's following a zigzag path. See, I will mark that. I will place this marker at the center of this ball. It's basically a light, reflecting a light, and I will move this marker with this ball or with this light. Okay? You can observe that this is following a zigzag path, a V-shaped path. See how it is. What is? So has it followed a zigzag path? Has it followed a zigzag path? See, it has followed a V-shaped path. It has followed a V-shaped path. Now let us see how it is basically. So according to you, when this clock is moving with respect to you, it does not follow the straight line path, but it follows a zigzag path, a turned V-shaped path. Okay? Is it following the same path?
Yes, sir.
It's following a zigzag path according to you. Now see how this zigzag path looks like. It looks like a V-shaped path. So here we will represent the time. See, this clock was moving with respect to you, and you have observed that the light clock, that the light pulse follows a zigzag path, a V-shaped path, turned V-shaped path. Now see, there are here you have again two events. First event is that light originates from the mirror, and second event is that light strikes the mirror, this lower mirror or sensor mirror. Okay, these are two events. Now see, in this clock, in this light clock, when you were observing this moving clock, you have observed that the light pulse follows a zigzag path. So it will definitely take some longer time to reach this, because in previous case it was this path, and now it is this path. So the light clock will obviously take some longer time to complete this path. And one more thing, here the two events, they occur at different positions. Okay, because light has originated from this position. Say it's x1, and it has struck the lower mirror at this position. Say it's x2. So the two events occur at different positions in this light clock, in this moving clock. In this moving clock. So now we'll calculate how much time does it take to complete this round trip. We'll calculate how much time has this light pulse taken to complete a one tick or a round trip. This is the round trip. It goes from here to this mirror and again comes back to this mirror. So this is one complete round trip of the light pulse. So we will calculate what is the time taken by this light pulse to complete this round trip according to you, because you are the observer. So let's calculate this time interval. Now see, this is light. This is basically light. Light is traveling in this direction, and we know that light travels with the speed of light. Light travels with the speed of light, because theory of relativity says that the velocity of light or speed of light is same with respect to all inertial observers. Okay, so light again the speed of light will be here c. It will be c. Let us say that this light pulse has taken time t. It has taken time t to complete this round trip. So according to you, this light pulse has taken time t to complete this round trip. So this time will be equal to, according to you, this time will be equal to this path, the total distance traveled by this light clock or light pulse divided by speed of light. So let us say that this position is this distance is this. Let us say P, Q, and let us say this R. So the total distance traveled by this light pulse is P R Q. So P R Q divided by speed of light c. So this is the time taken by the light pulse to complete one round trip according to u. Now I will calculate this distance. What this distance is basically. See, light clock takes, according to you, this light pulse takes time t to go from here to here and then from here to here. So total time taken by the light pulse to go from here to here and then here to here is t, according to you. Now see, from here to here and here to here, the distance, this distance is equal to this distance. This distance is equal to this distance. So time taken by the light clock to go from this point to this point is equal to time taken by light pulse to go from this point to this point. So total time is t, and the time taken by light pulse to go from here to here will be t upon 2. So time taken by light pulse will be t upon 2 to go from here to here, and then again equal to t upon 2 from here to here. So total time is again t. This plus this will again be equal to t. So this is the time taken by light clock, light pulse to go from here to here and then from here to here. Now we can calculate this distance. Can we calculate this distance? Because again velocity we define as velocity equals to distance upon time. So distance will be equal to velocity into time. Here the speed of light or the velocity of light is c. Velocity of light is c. So the time taken by the light to go from here to here is t by 2. So the distance covered by light from here to here is, it will be equal to distance equals to c into t upon 2. Similarly this will be also equal to c into t upon 2. So this distance is c into t upon 2, and this is also c into t upon 2. So this is the distance traveled by light pulse in one complete trip in a moving clock. So this PRQ will be equal to c into t upon 2 plus c into t upon 2 and divided by c. So this is the time taken by this light pulse to complete one round trip according to u. Okay. So this is the distance traveled by light clock. Now see, during this time t, as we know that this light pulse, this light clock is moving with velocity v in this direction. See, this light clock, the whole light clock is moving with velocity v in this direction. So during this time t, it will also go from here to here. Because this light clock will go from this point to this point during this time t. So can we say that the light clock travels the horizontal distance PR in time t? Is it that this light clock, the whole light clock travels the horizontal distance PQ in time t? Because in the same time the clock will go from here to here. So this clock will travel the horizontal distance of PQ in time t. So again we can calculate this horizontal distance. Can we calculate from the same formula? Distance equal to velocity into time. Here velocity is again, velocity of this clock is v. Velocity of this clock is v. And how much time does it take from P to Q? T. So we can say that this distance is equal to v into t. We can say that this distance is equal to v into t. So this distance PQ equals to v into t. So the whole distance from P to Q is v into t. Now see the distance. This is the midpoint of this distance. This is the midpoint of this distance. So we can say that from here to here and from here to here distance is same. So this distance is v into t upon 2, and this distance is v into t upon 2. So this half distance is v t upon 2, and this distance is v t upon 2. And this distance is L. That was given. So now you have a right angled triangle. You have a right angled triangle. You have this right angled triangle, say P, R and Z. P, R and Z is a right angle triangle. We take this right angle triangle. So this is our right angle triangle. In this right angle triangle, P, R, Z will apply Pythagoras theorem. Will apply Pythagoras theorem.
Sir, attendance.
We'll apply Pythagoras theorem to find out the time, to find out the relation between time in two inertial frames. So let me show you how we can calculate this. This is distance L. So from here we can calculate. Can we calculate it from here? Apply this Pythagoras theorem to this triangle. So when we will apply Pythagoras theorem to this right angle triangle P, R and Z, so we will write hypotenuse square, that is C into T upon 2 square, equals to base square V into T upon 2 whole square, plus perpendicular square, that is L square. Can we write this? By applying Pythagoras theorem to this right angle triangle, we can write hypotenuse square equals to base square plus perpendicular square. So this we can write as, see, you have T upon 2 whole square, T upon 2 whole square. We can take this T upon 2 whole square common in these two terms. We can write it like this, C into T upon 2 whole square, or write it like this, C square into T square upon 4 minus V square into T square upon 4 equals to L square. Can we write it like this? Can we write? Then take T square upon 4 common in these two terms. You will get C square minus V square into T square upon 4 equals to L square. Can we write?
Yes.
So here C square minus V square into T square equals to 4L square. Is it? So we have to calculate time T. So T square will be equal to 4L square divided by C square minus V square. Okay? So this is the relation. So from here we can write T square equals to 4L square. Here is C square minus V square. Take this C square common. From the denominator take C square common. So it is 4L square upon C square into 1 minus V square upon C square. Is it like this? So from here we can say C square. Can it? I will write like this: T square equals to 4L square upon C square whole divided by 1 minus V square upon C square. Can I write like this? Plus do again C square and 1 minus V square upon C square. So T square, I can write it 2L upon C of whole square divided by 1 minus V square upon C square. Okay? But as we know that when clock wire at rest with respect to you have calculated time, proper time, T naught, that comes out to be 2L upon C. So this 2L upon C can be written as T naught. So from here T square comes out to be T naught square upon 1 minus V square upon C square. So from here T equals to T naught divided by under root of 1 minus V square upon C square. And we know that, see, this 1 upon under root of 1 minus V square upon C square we usually denote as gamma, and this is called a Lorentz factor. This is called a Lorentz factor. 1 upon under root of 1 minus V square upon C square is called a Lorentz factor. So T equals to T naught into under root of 1 minus V square upon C square. So this is the time interval. This T naught is the time interval measured by you when the clock wire at rest with respect to you. And this T is the time interval measured by you on a clock which is in motion with respect to you. So from here, now see, from here we can say, see, you have under root of 1 minus V square upon C square. We have 1 minus V square upon C square. We can write it like this: 1 upon V minus C ka whole square. Can you write it like this? See, we know that this velocity, the relative velocity, it never approaches C. It never approaches, but it is never equal to C. But it is always less than C. It is closer to C, but not equal to C. Then the ratio V upon C. is it less than 1 or equal to 1 or greater than 1? It will be always less than, because this quantity is always less than this quantity. So we can say that the ratio V upon C is always less than 1. So this V upon C, this term here, V upon C is always less than 1. And if you take the square of its quantity, it will be more less than 1. It will be more less than 1. Then you have 1 minus a quantity which is more less than 1. A quantity which is more less than 1. So 1 minus something, it is always less than 1. So we can say the whole quantity under the square root is less than 1. So the square root of this that quantity is always less than 1. So the whole term 1 upon under root of 1 minus v square upon c square is less than 1. Now see, 1 upon under root of 1 minus v square upon c square. Since this term is less than 1, and if you divide 1 by a quantity which is less than 1, will you get a quantity more than 1 or less than 1? You will get a quantity more than 1. So this 1 upon under root of 1 minus v square upon c square is greater than 1. So this quantity is greater than 1. So we can say that the gamma is greater than 1. So gamma is a positive quantity, gamma is greater than 1. Now see, if gamma is greater than 1, so from your relation that we calculated t equals to t naught under root of 1 minus v square upon c square, we know that from here, now we know that t equals to t naught into under root of 1 minus v square upon c square. Or we can say t equals to t naught into gamma. And we know that this gamma is more than 1. So is this t naught greater than t naught? This t time t greater than t naught?
Yes, sir.
If gamma is greater than 1, then this time t is greater than t naught. So time t is greater than t naught. So this time t naught is greater than, this time t is greater than t naught. So the time interval you have measured in a moving clock is greater than the time measured by you on a clock which is at rest with respect to you. So we can say that time has become longer when the clock is in motion with respect to you. When the clock is in motion with respect to you, if you observe the time on that moving clock, you will observe that the time interval on that moving clock with respect to you has become larger. Or we can say in other words that that moving clock is making, so we can say, in other words, we can say that the moving clock ticks more slowly. That the moving clock ticks more slowly than a clock at rest. So the final conclusion of this time dilation is that we can finally conclude that from these relations, we can calculate, we can finally conclude an observer will see that a clock moving related to him ticks more slowly than a clock at rest related to him. So this is the conclusion of this time dilation. So the time interval on a moving clock with respect to an observer will become larger. Okay, this is the concept of time dilation. So this was the concept of time dilation, but this effect of time dilation is reciprocal. It is reciprocal. Reciprocal means Are you done? Shall I write this? So the effect of time dilation is reciprocal. effect of time dilation is reciprocal. What does it mean? See, the case I have discussed here, in that case, you were observer and you were observing two clocks. One was at rest related to you and another one was moving with respect to you. With respect to you, it was moving. So you were the observer. Now consider you are sitting in that spacecraft. You are sitting in that spacecraft and there is a clock in that spacecraft. So that clock will be at rest with respect to you because you are sitting in the same spacecraft. So that clock will be at rest with respect to you, and the clock which is on ground will be in motion with respect to you. So in that case, you will find out that the time interval on the clock in the spacecraft according to you is T0. That is for the proper time. And the time interval on the clock which is at ground. So according to you, the time interval on that clock will be T. Will be T. You got that? So in that case, proper time will be in which frame? In the spacecraft frame. Because you are observer there, you are observing now, and that clock on the spacecraft is at rest with respect to you. So we have discussed that a clock which is at rest with respect to observer, the time interval on that clock is proper time. So then proper time will be the time interval measured by you in the spacecraft, and the time that will dilate. So the clock which is at ground, which is on ground related to you, on that clock or that clock will tick slowly with respect to you. So with respect to you, that clock on ground will tick slowly than the clock which is at rest with respect to you. Okay, we got that. So the effect is reciprocal. Okay, so the effect of time dilation is reciprocal. This was the concept of time dilation.